In this video, we're going to take a look at avoiding common math mistakes. Now, there's many silly mistakes that students tend to make when working out a word problem or when working out a math problem. However, as an instructor, I simply chose the most common math mistakes that I tend to see in my students' work. So to get started, let's always remember that we should be consistent with our work. For example, if you had a rational expression and you multiply the top by something, you must also multiply the bottom by the same thing so that you're not doing anything wrong. So for example, with the 2 over root 5 number, it's actually improper to have the root in the denominator, so most instructors want you to simplify this so that the square root would be in the numerator. And so the trick here would just be to multiply this by root 5 over root 5. Now the reason that we can do this is because root 5 over root 5 actually equals 1. So you're multiplying this number by 1, which is why I say when you multiply the top by something, you have to multiply the bottom by the same thing so that you're not doing anything wrong. So if we multiply this number by root 5 over root 5, it would work out to 2 root 5 over 5. Now root 5 times root 5 is equal to 5. The square roots cancel each other out. So the idea here is if you multiply the top of a rational number by something, you should also multiply the bottom by the same thing. Now the same goes for equations. For the equation here, negative 5x plus 7 equals 3. Well, if you do something to one side of the equal sign, you must do the same thing to the other side of the equal sign. So if I wanted to solve for x here, what I would do is I would have to subtract 7 on both sides of the equation. And so I would have negative 5x. If I subtract 7 on the left-hand side, it cancels with this 7, and I have to actually subtract 7 on the right-hand side as well. So we subtract 7 from 3, which becomes negative 4. And also if we were to solve for x here, well, to get x by itself on the left-hand side, we would have to divide by a negative 5. Well, if you divide by negative 5 on the left-hand side, then you must divide by negative 5 on the right-hand side. So then we would have 4 over 5 as our answer here. Now with this last equation, the root x equaling 5, another common mistake is when we have square roots in our function and we're trying to solve for x. If you were to solve for x here, you would have to square both sides. And so a lot of students tend to forget that they need to square the 5 on the right-hand side. So likewise, what you do to the left-hand side, you must do to the right-hand side. So in this case, x would equal 25. Now with inequalities, lots of students tend to forget to switch your sign when you divide or multiply by a negative number. So for example, this expression here on the left, negative 5x is less than 10. If I'm solving for x here, I would have to divide by negative 5 everywhere. When you divide by a negative number with an inequality, you must switch this sign less than to be greater than, and divide negative 5 everywhere. We have x is greater than negative 2. Now if we take a look at the expression on the right hand side here, and here I don't have to divide by a negative number. So to solve for x, I would still have to divide by the number 5, but because it's a positive number, the less than sign must stay the same. And so my answer here would be x is less than 2. Brackets should be used to help us reduce those silly math mistakes that we tend to make. Now for example, in this expression 5 plus x times x, does that equal 5 plus x squared, or does it equal 5x plus x squared? Now if we were to just use brackets, we would understand what 5 plus x times x is actually equal to. So for example, the one on the left here, if I had brackets around this x here and around this x here, well then we would know that it's 5 plus x squared. However, on the right-hand side, if I had brackets around the 5 plus x, well then we would know that we have to FOIL the x through the entire bracket, and that would give us 5x plus x squared. Now the same idea here for negative 3 squared. Is it equal to negative 9, or is it equal to positive 9? Well, if we were to just use brackets, then we would have less of a confusion here. On the left-hand side here, if I had brackets around the 3, then that would represent negative 9. You're just squaring the positive 3, but there's still a negative out here. Now on the right-hand side, if I had brackets around the entire negative 3, and I square that, well, negative 3 times negative 3 is indeed positive 9. Now let's take a look at a rational function here. 3 over 5x. Well, is that equal to 3 over 5x, or is that equal to 3 over 5 times x? Well, again, if we just were to use brackets, then we would understand it more clearly. The one on the left-hand side, if I had brackets around the 5x, then yes, that would indeed be 3 all over 5x. However, the one on the right-hand side, if I had brackets around the 3 over 5 and not around the x, then that would mean 3 over 5 times x right here. So always use brackets just to make things clear, not only to yourself, but also to the person marking your work. Now here with notation, lots of students tend to get confused when they see sine squared. So on the left-hand side here, sine squared of x, yes, it equals sine x all squared, but sine squared x here does not equal sine of x squared. That's very different. Here on the left-hand side, you're squaring the entire sine function. Here on the right-hand side, you're just squaring what's inside, so you're only squaring the x inside there. Now the one on the right-hand side here could be rewritten as sine of x squared. You can bring the square inside that bracket there. These two here are the same. However, this one right here is still equal to sine of x all squared, which is very different. Now the same goes for ln x squared. If I were to have ln x squared here, that does not equal ln of x squared here. That's very different. The one on the left-hand side is actually ln x times ln x, and the one on the right-hand side, you're just squaring the x inside. Now another function that students tend to have a lot of confusion with is sine inverse, or arc sine x. Sine inverse x can be written as sine to the negative 1x, which does not equal sine x all to the negative 1. Those are very different. So the one on the left, again, is the arc sine function, or the inverse sine function. The one on the right here is actually 1 over sine x, which is actually equivalent to cosecant x. So it's very different. Cosecant x does not equal the arc sine x, or the inverse function for sine x. To avoid this confusion or reduce this confusion, your instructor should actually use arc sine x instead of sine to the negative 1 here. Now going back to ln x all squared not equaling ln of x squared. Now what I said on the left-hand side is that this is actually equal to ln x times ln x. And if you're ever confused about this and why this left-hand side does not equal the right-hand side over here, all you'd have to do is actually plug some numbers in. So for example, if x was 2, then on the left-hand side I would have ln 2 times ln 2. Now if you evaluate that in your calculator, you're going to get approximately 0.48. But on the right-hand side, if x was 2, then you would have ln of 2 squared, which equals ln of 4, which does not equal 0.48. It actually approximates to 1.39. So they're very different answers, very different functions there. Now these are very common math mistakes. Not everything is additive. So for example, root 4 plus 4 does not equal the separation of root 4 plus root 4. They're very different. Now again, if you're ever wondering or curious about why this is, well, we have addition under the square root. I mean, just evaluate this in your calculator. Root 4 plus 4 on the left-hand side here is actually root 8. Now on the right-hand side, root 4 is 2, plus root 4 is 2, and on the right-hand side you would get an answer 2 plus 2 of 4. However, on the left-hand side, root 8 is actually approximately 2.828. Very different answers. Now I think a lot of students get confused with this because of the addition versus multiplication. So for example, if I had root 4 times root 4 under the square root, that is equal to root 4 times root 4 because of the multiplication. If you have addition, you can't separate the addition. Not everything is additive like that. Now the same would go for here. If I replace those numbers with variables, well then same goes. Root x squared plus y squared does not equal x plus y. This is a very common mistake that students tend to make. They would actually take the root of x squared, which is x, plus, and then they would take the root of y squared, which is y, and so that's where they would get the right-hand side. But again, we have addition under the square root, and so you can't separate it like that. If we had, again, multiplication, then you would be able to separate it. So for example, if I had root x squared times y squared, then that would equal root x squared times root y squared, which is fine because again, you have multiplication. Another common mistake is the sign x plus y. A lot of students tend to try to separate that into sign x plus sign y, and that's not true. The x plus y is within the sign, which is not additive in this situation here. And again, if you're confused with this idea, plug in some random numbers for x and y and see if it's true. I mean, if x was 1 and y was 2, would this expression on the left-hand side equal the right-hand side if, again, x was 1 and y was 2? And you'll notice that it doesn't. Now, likewise for the expression ln x plus y, that does not equal ln x plus ln y. Now, in this situation, you'd actually have to apply your ln rules. So on the left-hand side here, ln x plus y is actually equal to ln x times ln y because of the addition. Follow your ln rules, and that would be true, and this does not equal ln x plus ln y. So those two are very different as well. Now there also seems to be a lot of confusion when we get into trig and radians versus degrees. Now you have to make sure that your calculator is in the right mode. Now degrees are often used in engineering and science classes, but radians are often used in calculus and higher math classes. So what's the difference with your calculator? Well, if you take a look at your calculator, sine pi by 2. Pi by 2 is 90 degrees. If you put that in your calculator and you obtain a value of 1, well then your calculator is in degree mode here. However, if you put sine pi by 2, again, which is 90 degrees, into your calculator and you obtain an approximate answer of 0.89399, then your calculator is in radian mode here. So if you're working with trig functions in a specific class, be sure to ask your instructor what they prefer your answer to be in, whether it be in degree mode or radian mode. And be sure to also understand how to use your calculator in converting from radian to degree mode as well. Now, factoring and expanding, there seems to be a lot of common mistakes with factoring and expanding. I've just chosen a select few here. My first one, 2x over x squared plus 1. This does not equal 2 over x plus 1. The mistake here was that the student would cross this x here with just one of the x's down here, and so that's how they would obtain this. However, x is not a common factor in the denominator, so you wouldn't be able to do that. In the denominator, if this 1 was instead an x, well then I can common factor an x out of the denominator first and then cancel that x with this x up here, and that would be true. So that's a common mistake. Now the one on the right hand side here, again, very similar to the one that we just looked at. A lot of students, well, because they see this and they see this, they think, okay, well, I'm just going to cross them out. But again, it's not a common factor. In this case, it's not a common factor in the numerator. So what students would do is they cross one of these with one of these, and that's how they would obtain this. However, like I said, it's not a common factor in your numerator. The only way that you would be able to cross those out was if you had a x squared plus 1 here, then you can common factor it out of the numerator and cancel it with one of the x squared plus 1 in the denominator. Now another common mistake that I tend to see is expanding. When we have a situation like this, a lot of students tend to forget that this negative is actually a negative 1, and you need to FOIL it through everything beyond it inside the bracket. So the negative needs to FOIL into the 5x and the 3, and a lot of students tend to forget that, so they make the 5x negative, but they forget that the positive 3 should also be negative because you should FOIL it through. Now this one's very similar on the right hand side. If we have 4 times x plus 2, again it's a foiling issue. A lot of students tend to forget you must FOIL into the entire bracket if you have multiplication. So not only is it going to be 4x, but it's also going to be plus 8. So the 4 should have been multiplied by the 2. Now in this situation here, another common mistake is with square roots. A lot of students tend to think that you can FOIL within a square root. You can't do that. The square root function is x plus 2 to the 1/2. Now, if you have an x outside, you would not be able to FOIL that through like that. It would be the same situation if you had, x plus 2 squared with an x outside. You wouldn't just FOIL the x through. You'd have to expand the x plus 2 squared and then FOIL the x through. So that's another common mistake. You cannot FOIL within a square root function. Now likewise on the right hand side, a very similar situation. A lot of students tend to try to FOIL the x outside of a sine function into this x here. This is not true. This would not equal sine of x squared. We actually can't expand the left hand side any further. It's very similar to the square root function where you can't FOIL the x into a square root. You also can't FOIL an x into a trig function as well. Now here, another common mistake is that when expanding a squared function, we kind of get lazy and forget our middle term. And so on the left-hand side, a lot of students just kind of jump the gun and say, okay, well this is then x squared plus 4. But we didn't expand properly. On the left-hand side, this is actually x plus 2 times x plus 2. So if we FOIL entirely, then you should get x squared plus 2x plus 2x plus 4, which works out to x squared plus 4x plus 4. And so we forget that middle term. I think the confusion comes from if I were to have x plus 2 times x minus 2, that would then equal x squared minus 4 because the middle terms actually end up canceling out. So be careful with that. Now another common mistake is common factors. So here on the left hand side, 4 is a common factor in both terms 4 and 4 sine squared x, so we can common factor a 4 out. And so the common mistake is that, well, students will common factor the 4 out, but they'll forget to take it out of the second term. Now the nice thing with math is that there's also checks that you can do. So for example, if I FOIL this 4 back through the bracket, will I obtain what I had in the first place? And in this case I wouldn't. I would get 4 minus 16 sine squared x, which does not equal the left hand side. Now with exponents, some common mistakes here are when you have rational exponents. So here x to the 3 over 2, a lot of students tend to write this as the cubed root of x, which is not true. X to the 3 over 2 is actually the square root of the cubed function x, whereas this one on the right hand side is actually the cubed root of x, so x to the 1/3 would be the proper exponent for that. That's a very common mistake. Likewise on the right hand side, when we have the square root of an entire function, a lot of students tend to make the silly mistake of not putting brackets around their entire function under the square root. And so the left hand side here doesn't equal the right hand side. If I were to have brackets around the 13x, then that would be true. But what I see here on the right hand side, if I don't have brackets, all I'm thinking is that the x is being rooted but not the 13. So be careful with that one as well. Another common mistake is the squared function. For x squared, a lot of students tend to forget that you need to square both the 4 and the x here, and so they write 4x squared as if only the x is being squared, but on the left hand side here it's actually the 4 squared, which is 16x squared. So that's another common mistake. Another one is with exponentials being multiplied. When we have exponentials being multiplied, a lot of students tend to forget that you're supposed to add these exponents here, and so they think that you should multiply the exponents to get t cubed, but on the left hand side here you should get e to the t squared plus t, which does not equal e to the t cubed. It's very different. Now another common mistake is this one down here, 9 times 5 to the power t. Well, on the left hand side here, it's just the 5 that's being raised to the power t, but a lot of students tend to think that they can FOIL the 9 and multiply it by the 5, and so we get 45 to the power t. We can't actually do that. 5 to the power t is an exponential. You can't FOIL a number into that. So on the left hand side, you can't really expand the left hand side. It would just have to stay as 9 times 5 to the power t. Now lastly, 2 sine theta squared. Another common mistake here is that we forget to square both terms. So we forget to square the 2 outside here. So the left-hand side here doesn't equal the right-hand side. The left-hand side here should be 4 sine squared theta. Now with rational expressions, dividing by the number 0 does not equal 0. So 2 or any number divided by 0 actually does not exist. So it does not equal 0. Left-hand side here does not exist. But 0 divided by a number actually does equal 0. So 0 divided by any value would equal 0. Now here with rational expressions, with the denominator here, a lot of students tend to try to split the denominator, and you can't do that. They get confused between this expression versus this expression here. Now the one on the right hand side here, yes, that is true. X is your denominator, and you can split that up because it's just the single variable x. And so yes, you can split this up as x over x plus 2 over x. That's true. However, on the left-hand side, if I have a function in the denominator, I can't split that up. This is not true here. Those two functions do not equal each other. Now there seems to be a lot of confusion between the square root of a number versus when you solve a function and you have to take the square root. Well, here the root of 25 is equal to 5. Notice that the value of the simplified radical is positive, so it's positive root 25. And so this is the only value of the square root, and the positive result is called the principal root. So the positive 5 gives us the principal root, while either positive or negative 5 might have been squared to get 25. The square root of 25 is defined only to be the positive option of positive 5. Now if we wanted the negative 5, then what we would do is the following. We would actually have to have a negative root 25, which is actually negative root 25. Now this equals negative 5, and the reason I'm putting these brackets in is to just clarify where the negative comes from. It comes from the negative outside of the square root here. Now when we're solving an expression like x squared equals 25, well, if I wanted to solve for x, then yes, I would have to take the square root of both sides, and then yes, that would give me the positive negative option of root 25. Now the reason that this is because you're trying to find all possible values that might have been squared to get 25. So here, yes, the answer is positive and negative 5 because you're solving for the value x. However, with numbers like positive root 25, we usually only worry about the positive square root unless it was otherwise written as positive negative root 25. Then you would give the answer of positive negative 5 there. Now down here, when we're adding two roots, a lot of students tend to forget that when you add two roots, they don't cancel the roots. That's actually when you multiply the two roots. So if this addition sign wasn't a multiplication, then yes, this would equal. That would be true. The two square roots cancel each other out. However, when we have addition, that's very different. This is actually equal to, because you have two of the same roots, that would be 2 root 3x plus 1, because you have two of them, the same ones. So that's very different than 3x plus 1. Now, like I said, if you are to multiply those two same roots, then yes, that would equal 3x plus 1. The two roots cancel each other out. Now with derivatives, the most common mistakes with derivatives is when using the power rule. The power rule simply states that we bring the 4 down in front of the x and we subtract 1 from our exponent. And so the silly mistake here is that we forgot to subtract 1 from the exponent, and so we should have had a 3 here. Now with exponentials, a lot of students get confused between an exponential and just a regular power function. For example, x squared is very different than 2 to the power x. 2 to the power x is an exponential, whereas x squared is not. So for x squared, yes, you would use the power rule like I showed up above, but for 2 to the power x, that you can't use the power rule, so this is not true. With exponentials, remember that the derivative of an exponential is itself, so it would be 2 to the power x, but multiplied by ln 2 here. So that would be the true derivative. Now of this next one, 1 minus 5x squared, if I were to take the derivative of that, a lot of students tend to forget the addition and subtraction rule for derivatives. You need to FOIL and take the derivative of each term separately. And so they forget that the derivative of 1 is actually 0. So this is not true. This 1 here should be 0. Now with rational exponents, a common mistake is to not subtract 1 properly from that exponent. Here we're applying the chain rule, and so that's fine. The 1/3 comes down. The function stays the same. However, we're supposed to subtract 1 from our exponent. Now because we see positive 1/3, they kind of make the silly mistake of writing it as, okay, negative 1/3. But what you should actually be doing is 1 minus 1/3 does not equal negative 1/3, right? 1 minus 1/3 actually equals 2/3. So this exponent here should be 2/3, not negative 1/3. But the rest of the work was done correctly. Now another common mistake with the chain rule here is when we go to apply the chain rule, we bring the 3 down in front, so the 3 comes down. That's true. The 1 minus 5x stays the same. That's true. We subtract 1 from our exponent, which becomes 2, and that's true. However, we forget to take the derivative correctly inside of your function here. The derivative of your inside function here is negative 5, not positive 5. So this here should be a negative 5.